All right, so we're very happy to have Sam Hopkins visiting us today and giving a series seminar talk. Sam is assistant professor at MIT ECS. He got his PhD from Cornell, and before joining MIT, he's a Miller Fellow at UC Berkeley. Sam is an expert on foundations of statistics, machine learning, sum of squares, semi-definite programming, among many other things. I met Sam at Robust Stats Workshop in 2018, where we shared an Airbnb, I remember.
Oh, yeah. I was really sick, yeah.
And all right, without further ado, I'll give you Sam. It's a whiteboard talk today also. So
yeah, thank you
you're
all.
in for a treat.
Thank you all for coming. This is like fresh, hot off the press. We just submitted this paper to Stock, so I haven't had a chance to make slides, which is why I'm giving you a whiteboard talk, but I hope it goes okay. So this is joint work with Ilias Diakonikolas, Ankit Pensia, and Stefan Tigo. I'll just jump into the setup and then talk about context once I tell you what kind of problem I'm interested in for this talk. So let's imagine that M is a matrix with real entries. It's D by N, and it's fat, so N is bigger than D. Now, let me remind you that an important quantity associated to a real matrix that we use all the time is the maximum singular value, or operator norm, of the matrix, which I will denote norm sub op, which is the maximum over unit vectors of the norm of mu. So here, this is Euclidean norm on the vector. This is Euclidean norm. This is max singular value. In this talk, I'm going to be interested in a sparse analog of maximum singular value, which I'm going to call the sparse singular value. That's non-standard terminology, but I've chosen it because it doesn't commit me to any one of the many applications of this idea. So I'm going to call for a parameter eta, which is a real number between 0 and 1, I'm going to call the maximum eta sparse singular value, SSV, of M to be the maximum over, again, unit vectors. But now I'm going to constrain this vector to have at most eta times n non-zero entries. I'm going to say that's eta n sparse of the norm of M times U. OK? So sparsity is fundamental across statistics and theoretical computer science and algorithms. I'm going to show you a bunch of applications of this thing. But now that I've told you some optimization problem, what would be the first kind of things we should ask as theoretical computer scientists? Is it polynomial time solvable? Is it NP hard? Can I approximate it? All the usual questions. So let me tell you a little bit of background. First of all, this is a very hard problem. If I think about it as a worst case optimization problem where the worst case input, over matrices. So for instance, if P is not equal to NP, then there's no FP task for this problem. That's maybe not the world's strongest kind of hardness, but if you make a bit of a stronger assumption, like small set expansion hypothesis, which is a close analog of the close cousin of the unique games conjecture, then there's no constant factor approximation. I think it's reasonable to conjecture that there's not even like a polynomial, like even n to the little o of 1 factor approximation is probably hard. That would be my conjecture, but this is what's known. This is due to Chen, Papadopoulos, and Rubinstein 16. So even though this is a pretty hard optimization problem, it turns out that a wide range of interesting average case problems, they can be average case optimization problems or other flavors of average case problems, actually reduce to average case versions of this problem. And so this talk is actually about average case versions of this eta sparse singular value problem. And it turns out that average case versions of eta sparse singular values are at the heart of a bunch of applications. I will talk about probably 2 in this talk, although there's many others. Let me list a few that you may have heard of. One is a problem called sparse principal component analysis. This is a data analysis problem where, given a high dimensional data set, your goal is to find a one-dimensional projection of that data set that explains as much variance as possible, subject to the constraint that that direction is sparse. Actually, that's like literally this problem where the data set is the rows of the matrix. Another problem is robust mean and covariance estimation. So estimating means and covariances of high-dimensional probability distributions in the presence of gross malicious outliers. Another example, which you may or may not have heard of, but I'll tell you what it means later in the talk, is computing the distortion of a subspace. Subspace distortion, not subspace, subspace. Another example for the real matrix norm connoisseurs in the audience is computing so-called hypercontractive norms of matrices. So say 2 to p norms. If you haven't heard of these things, no big deal. I'm going to talk in this talk, I think, about these two, assuming we get to both of them. OK, so at a very high level, this talk is about a new family of polynomial time algorithms for an average case variant of this eta sparse singular value problem that improves the state of the art for that average case variant, which I will define in a moment. And we obtain downstream consequences, improvements to the state of the art on all of these problems.
Just to look ahead here.
Yeah.
I mean, so far in this problem, you said you haven't introduced an adversary, whereas you're saying that it has application to these problems.
That's correct. Yes. Yeah.
Okay.
Yep. So it's not the how to get from this problem to these guys, especially this one is the adversarial one you're maybe thinking of. Yeah, how to get from here to here is not totally obvious.
Yeah.
I'll see if I can get there. Yeah. OK. So what's the average case variant I care about? There's always lots of ways to define an average case version of an optimization problem. I'm just going to tell you the variant I care about because it's the one that is most nicely fits at the heart of all the applications, although of course there are others. And the variant I'm going to care about, why am I changing color? There's no good reason for that, is certification. OK, so here's the game. And by the way, like almost any optimization problem, you can talk about an average case certification variant. This is not specific to sparse singular values. But in the context of sparse singular values, here's the certification problem. I'm going to give you a random matrix. So by that I mean, let's say it has Gaussian entries. So just independent standard Gaussian entries. Our results don't actually rely on Gaussian, but just for simplicity in this talk, let's make it Gaussian. And your goal is to output some number, let's say alg of m. So you're supposed to do this in polynomial time. And the rules are that with probability 1, like all the time, you always output an upper bound on the sparse singular value. So eta is some parameter that your algorithm takes, and I'm suppressing the notation. So you always output an upper bound, no matter what m I give you. Random, fixed, worst case, whatever. And then the goal is to minimize the size of the upper bound you output. So of course, you could always output some trivial upper bound, but that wouldn't be a very interesting algorithm. My goal is to output the smallest upper bound that I possibly can, on average over the choice of m. So this expectation is over the randomly chosen m. OK, that's the game. Questions about the problem?
I don't even understand the statement yet. So
Great.
the goal, ordinarily, I would say the goal once the input was decided. But
Sorry. Maybe I should say, how do I measure the quality of an algorithm? What would be a good algorithm?
I see.
Good algorithms, a good algorithm,
I see. Got it.
that means small value. Like I want to output good upper bounds, tight upper bounds, as tight as I can. OK?
But again, you're not. This isn't comparing to the right value on a per instance basis. It's not.
That's right. I'm not comparing on a per instance basis. I mean, I am. This is like the usual notion of relaxation. That's per instance.
Yeah.
This is on average over the ensemble.
Yeah, okay.
That's right. Yeah. Further questions? OK, good. So let's get a sense, though, of what the typical, like first of all, what would be a trivial upper bound, and second of all, what is the truth? Like what is the actual high probability value of the sparse singular value? Okay. Actually, the statement for the actual value over the randomly chosen m is a little bit complicated, so I'm going to give you sort of a qualitative version of it rather than giving you the full quantitative expression. That'll be enough for this talk. But before I tell you the actual truth, let's think about a trivial upper bound. Okay? Or maybe it's not completely trivial. Well, I reminded you that the maximum singular value is sort of is a relaxation, or let me remind you that it's a relaxation of the sparse singular value, right? So this value for any matrix M is always larger than this one. And so one algorithm, and I can compute singular values in polynomial time. So one thing I could do is just output the maximum singular value, right? So what would that give me? So what is, can you guys see this pen? Is it too faded back there? Is it OK? It's OK. So how does this do? I could output the max singular value. Well, if you take some random matrix theory,
here's some fresh pens.
oh, fantastic.
Yeah, so we don't want that.
Juicy, juicy, fresh pens. Thank you.
We have them.
Don't worry, I have to. It's much harder at MIT to get fresh pens. It's impossible.
I recall that.
Yeah. It's. Oh wow, that's so good. I have my own personal stash of them in my office actually, because they're impossible to get anywhere else. Anyway, okay. So how big is this? How big is this number? Well, it turns out that if you have a random matrix with Gaussian entries, then the maximum singular value scales like the square root of the length of the long dimension. That's a basic fact from random matrix theory. And so this, we know the constant, but I'm not going to bother writing it for this talk. This is like theta of square root n. Okay. So is that the truth? Is it not the truth? What's the true value here? Well, let me tell you that for any, if eta is anything less than a constant, right? If eta is a constant, then actually the sparse singular value will act kind of like the ordinary singular value, because you're not making too big a restriction on the vector u. But if I start restricting u to be sparser than a constant fraction sparsity, the sparse singular value, this optimization problem is getting more and more restricted. And so the true value will get smaller and smaller. And it turns out that as soon as eta becomes subconstant, the true sparse singular value is also little o of root n. And I could write out the actual value, but it's just going to be a distraction, so I'm not going to for this talk. It's smaller than the operator norm. And so I'm going to now set a goalpost for what I'd like my algorithms to do, a very concrete one. And I've chosen it because it's relevant to all of these applications. I'm going to call a certification algorithm non-trivial if it beats the maximum singular value. Right? So maximum singular value would let me certify root n. I want to beat root n asymptotically. That's my game. Cool? OK. So let me tell you about the state of the art, and then I'll tell you our result. And then we'll get to the connections to a couple of these problems. So what's the state of the art here? It turns out that this basically, even though nobody quite writes the problem like this that I know of, or it happens sometimes in the sparse PCA literature, maybe not so much in these literatures, it turns out that because this problem is at the heart of all these applications, people actually studied the heck out of this. And there are basically two interesting algorithms here that are non-trivial. And they were all rediscovered like several times. So here are the two. I'll tell you what guarantees those algorithms achieve. So first, there's what I think is a folklore algorithm. It appears in a lot of places, which is non-trivial when eta becomes quite small. So if eta is very small, turns out less than 1 over square root dimension, and this swiggle less than is going to hide log factors for this talk. If eta is less than 1 on root d, then you can be non-trivial by some algorithm that involves computing sums of inner products of rows and columns of this matrix. I'm not going to describe it explicitly because it won't play a big role in this talk. But some relatively naive algorithm becomes non-trivial. Then there's another algorithm, which I think first appears in a paper by Barak, Brando, Harrow, Kellner, Steurer, Zhu from 2012. And their algorithm is non-trivial under the following condition on the side lengths of the matrix and the sparsity level. The long side has to be at least, I should have a squiggle, eta times the square of the short side. So let's pause for a little bit of intuition. As you vary n, d, and eta, when does this problem get easier? When does it get harder? Okay, so first of all, let's think about eta. When eta gets smaller, this problem gets easier, right? Because all I want to do is, I'm not comparing to the truth, remember? I'm comparing against this fixed benchmark of root n. And as eta gets smaller, this optimization problem gets more and more and more restricted. So the truth gets smaller and smaller. It should be easier to certify an upper bound on that value. So that's good. That's borne out here, right? Eta gets smaller, this condition gets truer. Eta gets smaller, this condition gets truer. OK, good. What about n? Well, this is a little less obvious, but as n gets bigger, the problem gets easier. That's what we see in this expression. What is going on here? Well, if you think very, blur your eyes kind of intuition about this, as n gets really big compared to d, this kind of starts to act like a vector and not a matrix, right? In the limit that n is getting enormous. And for this problem, when n is just a vector, this is actually easy, right? What do? I take just the top k coordinates of that vector, or the top eta n coordinates of that vector. OK, so as n gets bigger, this problem gets easier as well. So we see that borne out in these cases. OK, so whatever, that's some algorithms. What about hardness? Well, this is an average case problem. Hardness for average case problems is always a bit sticky. And there's various things you could try to do. The best hardness evidence that I know is, for this problem, involves proving an unconditional lower bound against a broad family of algorithms, which in particular includes these algorithms. You could phrase this as a so-called statistical query lower bound if you want. I won't get too in the weeds about what the model of computation is. If you've heard of these low-degree polynomial tests, that would be the model. This is due to Mao and Wine, 21. And they gave some evidence, I actually believe this evidence, that this problem probably is hard if, hard, maybe question mark, if n is less than eta squared d squared. OK. So unless anybody wants me to get into the weeds about it, I'm not going to get into the weeds about exactly what this notion of hardness is. Let's take it for granted for this talk. So they prove some lower bound that suggests that you can't do that much better than this algorithm. You can pick up an additional factor of eta. But it turns out that this factor of eta is actually rather important for these applications. And the state of affairs is, to me, unsatisfying, this state of affairs. One thing you can see is that this algorithm, which seems more sophisticated than this one if you look at them, doesn't actually recover the guarantees of this one in the limit, right? If I put eta to be 1 over square root d, this thing becomes d 1.5, which is still a stronger assumption than I wanted to make. I wanted to just say that n was the long side. OK. So now I can tell you our result. For every epsilon, we give a polynomial time algorithm, which is non-trivial if n exceeds eta squared d to the 2 plus epsilon. OK. So up to this epsilon in the exponent, we close this gap and recover what should be, we think, the weakest condition on n, eta, and d under which you should be able to give a non-trivial algorithm in polynomial time. Again, up to this epsilon in the exponent.
I'm going to guess that the degree of the polynomial depends in On the epsilon?
Yes. So the runtime scales like n to the O of 1 over epsilon. And that does mean that if you take epsilon to be slightly subconstant, like 1 over log, in quasi-polynomial time, you can get this to look like eta squared d squared up to logs. So OK, so there's still something to be done about the difference between, say, quasi-poly and polytime here. But other than that distinction, this closes the gap and should be the best you can do for, we think, for non-trivial algorithms for this problem. Yeah?
So you defined a notion of an algorithm to be good.
Yes.
You claimed that these algorithms are practically important, so they're, at least the previous two are probably implemented in software that people use. So
This one, yes. This one.
So how are the algorithms compared to decide which one to use in practice?
Oh, I'm the wrong guy to ask that question. I don't have a great answer for you. I think that OK, what I guess the best answer I have is that of these applications, this is the one where people have done, I think, by far the most experimental work. And here, what one does is look for the objective value that you can achieve when you're solving the optimization variant of the problem, right? Like, please find me a U which achieves a large value, which is somewhat different from the certification version, although often these certification algorithms can be turned into optimization algorithms. But I don't.
Which is the winner?
Oh, I have no idea. I mean, I think it's almost certainly context dependent. Like, I don't have a consistent answer for that. Oh, yeah. Sorry.
Is there anything non-trivial known for FPT algorithms for this? Like, if eta ends a constant, then the whole thing is easy?
No, if eta n is a constant, well, sorry. You mean for the certification thing, or you want the worst case version?
I mean, even the worst case version, but yeah. I mean, if eta ends a constant, the worst case version, can't I just project down to all my guesses for?
No, if eta times n is a constant. Yeah. That's easy. That's
like non-trivial things known, I guess, for either worst case or average case.
For average case, there are some non-trivial trade-offs between, like you can beat that brute force algorithm for the average case.
Okay. So if it's like 10 or 20, you could still solve it potentially.
Maybe 20 might be big,
Yeah.
but yeah.
That's a good question.
Okay. Applications?
Yeah.
Yeah, let me say something about applications. Okay, so let me start with this one. Okay, robust covariance estimation. So what's the problem here? I'm going to give you samples from, let's say, a Gaussian distribution for purposes of this talk. Except some eta n of these samples have been potentially corrupted by a malicious adversary. Okay, so this is like a zero mean I can assume without loss of generality by pairing samples and subtracting them from each other. So I have some unknown covariance sigma, and eta n of these samples were corrupted maliciously, the others are clean. And my goal is to take these corrupted samples and find some matrix sigma hat such that I get a spectral approximation to sigma. So 0.99 sigma hat is a lower bound on sigma, is an upper bound on 1.01 sigma hat. Okay. Obviously, 0.99 and 1.01 are arbitrary choices here. So this problem has been studied intensely in the algorithmic robust statistics world for the last nearly 10 years. Let me tell you something about the state of the art, because actually the number of samples that you need to solve this problem in polynomial time was so far not known. So if you're willing to spend exponential time, you could still ask, okay, I clearly need more than one sample to do this, right? I need more information than that. So even in exponential time, there's a non-trivial question here. How many samples do I need in order to find such an estimate? It turns out that the number of samples you need is just at least d for any small enough eta. So eta just has to be less than like some universal constant. And then I can get away with order of d samples, which actually is no more than I would need even if eta was 0. I would still need d samples. But we don't know how to do this in polynomial time with a number of samples that scales linearly in dimension. Okay, in fact, until fairly recently, like 7 or 8 years ago, we didn't know how to do this in polynomial time at all. So that's a fairly recent innovation. But now that we know how to do it in polynomial time, we can ask, okay, what's the actual number of samples I need to do so? Well, the best known things one can do in polynomial time bear a remarkable similarity to these two state-of-the-art algorithms. Either you can do it with linear in d, but eta has to be less than 1 over root d. This is based on basically like taking xi's who just look like obvious outliers, they're too big in norm, and throwing them away. Or there's a less naive algorithm that actually uses this as a subroutine. You can do it with eta d squared samples. Okay, so what do we get? In our case, no big surprise. I've written the numbers already. Basically, oh, by the way, I should put citations here. This is basically folklore. This application of this algorithm is Kothari-Steinhardt 17. Sorry, Kothari-Steurer 17. What do we get? No big surprise. For every epsilon bigger than 0, we get a polynomial time algorithm that uses only eta squared d to the 2 plus epsilon samples. Us. Oh, I already said that.
Does the runtime for the other one depend in a bad way on
this runtime?
Yeah.
I do. What's your definition of bad? I mean, I assume this is in your definition of bad.
That's bad. That's bad.
Yes. No. This is not bad in this sense. It is okay. It is bad in the sense that it involves. Actually, no. I guess here by now we know versions of this that run reasonably fast. In fact, I was just talking with one of your students this morning about this. Yeah. Hi. There you are. Sorry. So actually, the best known running time for this is d to the 3 point something involving a fast matrix multiply. So this is not so terrible. Like you could, and okay, if you use like actual matrix multiply and not some silly fast matrix multiply, you can hope to run this. This not so much yet. Yeah. Okay. So the connection between this thing and between the sparse singular value problem and robust covariance estimation was certainly in prior work. This is not due to us. We can really plug in our new sparse singular value algorithm into the existing framework. But just because I think it's probably on your minds, let me try to give you some idea of what the connection is supposed to be here. So if I'm doing covariance estimation and I'm worried that there's some eta n fraction of samples which might be screwing me up, one way to phrase that worry would be if is there a way to remove eta n of these samples and significantly change the empirical covariance? That would be bad news. Okay. So one thing that you might want to check if you're inside the guts of a robust covariance estimation algorithm, you might want to be able to detect whether that has happened to you. Right? Do you have a set of samples where some eta n of them can be removed and significantly change the empirical covariance? So now imagine that those samples are the columns of this matrix. Okay? It turns out that the maximum norm that you can achieve over a sparse vector put here, if we count dimensions, if I put a vector here, it has one coordinate per sample. That maximum norm will be the maximum variance that you can achieve by taking any subset of A to n samples and picking the maximum variance direction among those samples. Okay. So what these robust covariance estimation algorithms do is take their samples. They try to certify that there's no bad subset, no bad small subset. If there is no bad small subset, they're done. They output the empirical covariance. If there is a bad small subset, then they have to do something. They will try to find which vectors are contributing to that subset and try to throw them out or downweight them or something. So there's a whole framework here that wraps the sparse singular value algorithm to do something in addition. But all we needed to do to improve the sample complexity was improve the sample complexity of that component. And that's what we did. OK. I'm not going to speak more about that application. But if there are questions, I'm happy to answer them. Yeah?
Are the samples scalars or vectors?
These are vectors. They're in. Sorry, I should have said. Thank you. This guy is in. This is d by d. So I have a d-dimensional covariance matrix. Sorry. Thank you. Thank you very much. OK. Let me tell you about a very different flavor of application from a very different part of computer science. Subspace distortion. OK. So as before, I need to this one bug of this talk is it has a lot of definitions, which I'm trying to not do all of these applications because that will really kill us. But we'll do one more round of definitions. So when do we go to, by the way, to like 55 or something?
Yeah.
OK. Cool. So suppose you have a subspace of Rn. Okay. Here is a important quantity that is associated with this subspace, which measures how close the subspace is to containing a sparse vector. So this is not our definition. This has been around for 40, 50 years. The distortion of a subspace is equal to the maximum over vectors in the subspace of some appropriate scaling times the ratio between the Euclidean norm and the L1 norm of the vector. And if you play with this for a little while, because L1 norm is some nice analytic relaxation of sparsity, this basically measures, this you can do a little work and see that this is a number between 1 and root n, just by some Cauchy-Schwarz. And it's large when the subspace contains or is close to containing a sparse vector. Okay. So it turns out that subspaces of Rn that have relatively large dimension, of course, if I go all the way up to all of Rn, I'll contain sparse vectors, so my distortion is fairly large. But if you can get relatively large dimension without containing or being close to containing a sparse vector, those subspaces are useful. They have a number of applications. So this is not the point of the talk, but low distortion subspaces are useful for error correcting coding over the reals. They're useful for compressed sensing. They're useful for approximate nearest neighbor search. So there's a whole line of literature on trying to find low distortion subspaces of the highest possible dimension. Right? The higher the dimension of the subspace, the harder it is for it to be low distortion because it contains more vectors, but the more useful it is for downstream applications. So as you might expect, oh yeah?
Sorry, I think I just didn't catch the connection to vector sparsity.
I didn't tell you yet.
Oh, okay.
I didn't tell you yet. This is something else, right? So one of the cool things about this talk is that this problem doesn't look obviously connected to most of these. Okay, maybe it's obviously connected to this one, but the rest of them it's not so obvious. Yeah. But okay, I can just tell you. The relationship is we're going to think of this subspace as the row span of the matrix. Okay. So, good. Where was I? Random subspaces shouldn't come as a big surprise, of dimension up to even 0.01n have basically the best possible distortion, constant distortion. So random v up to d could be like 0.01n have distortion order 1. But if you want to know whether a given subspace that you sampled actually has that distortion, now you're in the certification business, right? So it turns out that you can run our algorithm where you view the subspace as the row span of the random matrix, right? The row span of this random matrix will be a random subspace. And if I give you a subspace, I can just take a random basis for it and stick it in here as the matrix. And you can produce a certificate that the subspace is not close to containing sparse vectors. Okay, so I could write out some formula that's a relationship between n, d, and eta, but I've written it already a bunch of times. And like for the other problems, we basically are tight against this style of lower bounds for this subspace distortion problem as well. Is that a question or a stretch? Okay.
I do have a question.
Yeah.
Is it important that the basis you choose be a random basis or just any basis? Do you benefit from
I don't
having
know.
a random basis of the?
I don't think so.
Okay.
I think
You
any
said
basis would be
random,
fine.
I wouldn't
Yeah,
say that
yeah,
was
yeah. No, I think it's not significant. I think it's not significant, but don't hold me to it.
Okay.
Okay. I have circa, yeah.
Oh, I guess I have two questions. So one question is, for these applications, is it important that the subspace you're using is random? And the second is, for these applications, do you actually need to be able to certify, or does this just allow you to like promise that your algorithm is like correct at the end of the day when you plug in or something?
It should be the latter. I mean, the argument that people sometimes give here, for instance, is that like, okay, for compressed sensing, I don't know how much I believe this argument, by the way, but this is what people will say. For compressed sensing, the subspace that's relevant is going to be the kernel of your sensing matrix, right? So you're like getting an underdetermined linear system. So the matrix has a kernel. And the argument people make is, well, like you're making an imaging device. You're going to like bake this sensing matrix into hardware. You're going to make a million units of the hardware. Like it's a very expensive mistake if you got it wrong. You'd really actually like to know, is that particular matrix good? Yeah, I don't know how much I believe it, but okay. I have 10 minutes, so I'd like to talk about the algorithm. Cool. So in the paper, we write the algorithm, and we'll have this on archive very soon. A classic promise. No, we really will. In the paper, we write this in this sum of squares hierarchy language using semi-definite programs, and the fact that it can fit in that framework is actually important for like plugging into the existing frameworks for these kind of problems. But because I just want to tell you about the certification algorithm, I'm not going to phrase it that way to avoid an even bigger avalanche of definitions. What the algorithm is going to do, or the way that I'll phrase it in this talk, is given the matrix M, it's going to assemble some list of not too many other random matrices, really big ones, like with this kind of dimension. It's going to assemble, it's going to compute some list of matrices, say A1 through A, this will be some number. This will be like maybe x of 1 over epsilon or something. So not too many matrices. They will live in large but still polynomial dimensions. And it will compute the maximum eigenvalue or maximum singular value of each of these matrices. And then it'll combine them into these singular values in some way. So take some linear combination of these maximum singular values will turn out to be an upper bound on the eta sparse singular value of M. raised to some appropriate power, roughly 1 over epsilon. Okay, so this is the outline of the algorithm. Build some matrices, compute eigenvalues, combine the eigenvalues in some simple way. So in my remaining time, I want to try to show you what these matrices look like and convince you that there would be some way to combine eigenvalues of these matrices to get such a bound. Okay, so now we get to do some math. Let's go ahead and write out sparse singular value again as an optimization problem. Max over u is eta n sparse, norm of mu. I'm just going to manipulate this problem a little bit to get to, well, actually, what I want to get to is something involving the variance that you can get from columns of the matrix. So something we actually already talked about over here. So you can write this as the max over u is eta n sparse, and v is just some unit vector of inner product of v with mu. That's the same because of Euclidean norm. And this guy, well, I could write max, I'm going to drop this stuff, m transpose v u. Okay. So now let's think about where the optimizer of this is achieved. If I have a fixed v, right? If I have a fixed v, then the optimizer of this is going to be given, the optimizer over u is given by taking the largest eta n coordinates of the vector m transpose v, right? It'll just stick all its mass there, and it'll give me, at the end of the day, I'll get the L2 norm of the largest k coordinates of this vector m transpose v. Now let me have some notation. I'm going to give names to the columns of m, xn. This is d by n. Okay. So the coordinates of m transpose v are the inner products of the columns of m with the vector v. Right? So what am I looking for? I'm looking for a vector in d dimensions and a subset of eta n coordinates where I measure the L2 norm of the vector restricted to those coordinates. Okay. Just a bunch of series of equalities so I can phrase this in the way I want. Cool? Okay. This is the operator norm of a matrix induced by the subset S. Max V in RD. Sorry, no V. That was the whole point. Max over S now, just the subset of coordinates of the operator norm, because this is V transpose times summation xi transpose times V, summation I in S, xi transpose. Okay, maybe with a 1/2 here. So now what's the game? I've said the game, actually the sparse singular value thing was the whole time in disguise the problem of finding the subset of columns of M with the largest empirical covariance. Actually, I already sort of said that over here. We used that already implicitly. So now let me remind you of an important inequality that relates the operator norm of a matrix, any matrix, to some simpler function of the entries of the matrix. For any matrix A and any integer p, one has that the operator norm of A raised to the 2pth power is bounded by the trace of AA transpose to the p. Right, why is that? Well, the eigenvalues of AA transpose are the squares of the singular values of A, and when I take AA transpose and go to the p, I get the pth powers of those eigenvalues, and I take the trace and I get the sum of the pth powers. So this is the pth power, or the 2 pth power of the top singular value. And this is the sum of 2 pth powers of singular values. OK, so let me apply this inequality to this expression, to this matrix. So this guy, continuing from here, this is at most the max over S of the trace of summation I in S xi transpose to the pth power. And then I guess I have a 1 over 2p outside. OK? So for any p that I want, this is true. And I'm going to eventually choose p to be 1 over epsilon, but no big deal for now.
Okay.
Where did this p come from?
Trying to bound this quantity,
Yeah.
which doesn't have a p in it.
Well, I raised this to the pth power.
Okay.
I applied this inequality, and then I took a 1 over pth root.
Okay.
Yeah, yeah. So and p was something I got to choose. So this would work for any p.
I see.
OK. Good. So OK, this is getting crazy. But what is this thing? All right. Now instead of a maximum singular value, which is like a complicated function of these underlying x's, I have some much more explicit function of the x's. OK, I've still got this maximization over an unknown set, but bear with me. So let me literally write out what this function is. It's actually not that bad. When you take powers of matrices, you take walks. All right, so what does that notion of powering of a matrix do to this? Max over S. Here's what this will be. You take a sum over a sequence of indices, I1 up to IP, in the subset S. And then you take the inner products of the x's around this kind of cycle of indices. So I get like xi1 inner product xi2, xi2 inner product xi3, and so on, xip inner product xi1. And this all better be to the 1 over 2p. OK. So now I have some horrific but kind of scalar valued optimization problem over the choice of this subset S. Right, and I want to put an upper bound on the maximum possible value here. So now I'm going to, in my final 3 minutes, describe what one of these matrices look like, and then hint to you how you would get more than one matrix. All right. So how could I get an upper bound on the value of this thing? Now I'm going to do a trick. This whole talk is just a sequence of equal signs. I'm going to write this in terms of the indicator vector for the subset S. I'm allowed. So instead of summing over the indices in S, I could sum over all the indices, I1 to IP and N, and I could put the indicator that I1 is in S, indicator that I2 is in S, up to the indicator that IP is in S, and then multiply by this big sequence of inner products that I have out here, xi1, xi2, ... OK, again, not maybe obvious why I would want to do this, but it's allowed. OK, here's the punchline. This is the quadratic form of a matrix evaluated at a particular vector. What vector is it? It's a giant tensor power, Kronecker power, of this indicator vector. X over S. Indicator vector for the subset S, tensored up p over 2 times. Transpose. Some gigantic matrix. So this is like n to the p over 2 by an n to the p over 2 size vector. It's huge, but polynomial size. Times the indicator tensor p over 2. 1 over 2p. And what is this matrix? Well, it's indexed by subsets or by tuples of the indices. So it's got a row and column, like if at entry I1 up to IP over 2 in the row, and IP over 2 plus 1 up to IP in a column, the entry of this matrix is this gigantic product. Product of all kinds of all this gigantic inner product. Okay. Finally, this means that I can get an efficiently computable upper bound on the sparse singular value, because the maximum of a quadratic form is at most the maximum singular value of this matrix times the L2 norm of the vector that I'm evaluating the quadratic form at. Right? So just destroy my board work here since I don't have much time anyway. This is at most, maybe we can call this matrix B. The operator norm of B to the 1 over 2p times the L2 norm of this vector. This is the indicator vector for a set of size eta n, so it has L2 norm root eta n. And then I raise that to the pth power, and I take a 1 over 2p, so I think I'll get eta n probably to the something. Who knows? Some appropriate constant there. It's hard on the whiteboard, you guys. OK. So this is the flavor of how you get an efficiently computable upper bound on the maximum sparse singular value from the eigenvalues of large but polynomial-sized random matrices. All right. Now, why doesn't this just work? This actually isn't the right thing to do. It's not quite the right thing. It doesn't prove our result. The problem is that if after we've gone through all of this, you can analyze the expected operator norm of this matrix. You can do some random matrix theory on it, and it's too big. So this will not give you a non-trivial algorithm, sadly. But you can tweeze this matrix apart. Okay, you can do surgery on this matrix. And what's going on is that the large eigenvalues of this matrix are associated with directions that are not uniformly random. They're directions that we can actually write down, and they're not well aligned with vectors that have the form tensor power of an indicator vector of a subset. And so what we do is do surgery to take apart this matrix, to write it in terms of smaller random matrices, smaller in operator norm, where we can bound just the maximum operator norm as a random matrix, and matrices that have some structure, and we can show that that structure makes them not align well with this, so we can beat the norm based on their operator bound, beat the bound based on their operator norm. Okay, so ultimately, instead of one matrix, one ends up with about 1 over epsilon to the 1 over epsilon of them. No big deal, epsilon's a constant. You build all these matrices, compute their eigenvalues, put them together by pretty much just taking sums and roots, and that gives you a certifiable upper bound on the sparse singular value. Okay. Thank you for your attention. I will say one or two interesting open problems. Maybe, actually, let me say one, two open problems. One would be, obviously, do you need this 1 over epsilon? Can you get anything useful or practical or even remotely hope for that out of this kind of thing?
Or do you need the n?
Or do you need the n? Yeah, or do you need the n? Exactly, yes. Good point. So can the running time be improved? Another is, for this whole talk, I set this goalpost of non-triviality. I said all I want you to do is beat the upper bound on the sparse singular value that's afforded by the max singular value itself. But of course, there's a more fine-grained question here. I could ask you, what's the best upper bound you can certify? How small is that little o of root n? And that question is a lot more complicated, from what I can tell. And we actually don't have matching upper and lower bounds for that problem. So even though we quantitatively are getting little o root n exactly when we think we should be, we're not getting the right little o, as far as I know. So thank you for your attention. I'm around for the afternoon. Thanks for the questions. Really appreciate it. And I'm told we'll be kicked out summarily at 1.
Well, I don't
yeah.
see any other students out there waiting. Where does the n?
Why is there n to the?
Why is it n to the power instead of c to the?
Oh, because of the dimensions of these matrices.
Yeah.
Like if I just writing this thing down,
Yeah.
right? This is end of the p over 2 by end of the p over 2.
Right. Because there are all these techniques I know in the old.
Uh-huh.
Yeah. Anyway,
For what did you have in mind?
in the case of rounding, let me ask you later.
All these like SOS techniques that get from like the things that let you do degree r SOS in like 2 to the r instead of n to the r, this kind of thing. Yeah. I don't know how to do that for this kind of sum of squares proof. Like the reason is that the proof involves dense polynomials. So the reason that those techniques work for certain problems is that the dual solutions that you're using, dual solutions are like polynomials, and the dual solutions are sparse polynomials in those contexts. We'll do it offline. Okay.
Because I'd love to hear that.
Sure.
I'm
Sure. Happy to discuss.
Okay.
Okay. Let's see. I'm supposed to try.